Hi, everybody. I just wanted to make a quick video that goes through kind of how to approach um, whether or not to use the perpendicular force or the perpendicular radius. So here we have kind of a setup, and I'm literally just going to focus on this force of tension right here. So that force of tension, um, that is going to be applying a torque to this drawbridge. And so we're going to talk a little bit about, okay, how do we calculate the perpendicular force and how do we calculate the perpendicular radius? So let's start with the perpendicular force. That is going to require us to draw a few additional triangles here. And this is one of the reasons why I think for this particular problem, I don't find the perpendicular force to be as easy and intuitive as the perpendicular radius. So we have this force of tension, and in this problem, it's 5,000 newtons, just a value that's given. This is the force that we actually need to use. This perpendicular force, and that's a tension force, that's perpendicular to the actual rotation of the drawbridge around that axis of rotation. And we're given this 50-degree angle here. And so here we know that then if this angle is 50 degrees, that means this angle here is going to be 40 degrees, which means this angle here is 50 degrees. Now, I need my force of tension here that I know. That's my hypotenuse. So I know that my force of tension that's perpendicular is 5,000, and this is adjacent to that hypotenuse, cosine of 50 times the length of this drawbridge, which in the problem it's given as 8 meters. So I'm just going to say 8. But it would be any R value that you need. So these are some of the values that we've been given. And this sets up not just our perpendicular force, but when I add that 8 meters, that gives us our torque, because I've got my perpendicular force times my radius. That gives me my torque. Now, that required us to draw not only this or identify this angle, I had to identify this angle. I had to correctly draw this adjacent side, make sure I drew it correctly so that I could intuitively figure it out that this is the hypotenuse and this is the adjacent side. I just think that's kind of too many triangles to draw for a problem like this. And so that's when I think, hey, the perpendicular radius is actually an easier value. So to identify the perpendicular radius, we first, again, got to identify that axis of rotation for a problem. I'm just going to draw an imaginary line through that axis of rotation. Now I know that my force of tension is up here, boom. And now I can see that my force of tension is going to directly go through that imaginary line through that axis of rotation at a perpendicular right angle. So if I were to extend this out, yeah, that's going to form a right angle. So that distance would give me what I'm going to call my perpendicular radius. And whenever you have a force that's directly left to right or directly up and down, like if I had the weight of my drawbridge as one of the torques I need to find, then that force is directly up and down. That's going to form a right angle with an imaginary line that's easy to draw. Whenever you have something like that, it's typically easier to use the perpendicular radius. And that's kind of a rule of thumb that usually applies, might not necessarily all the time, but in problems like this, it usually applies. So let's get rid of that other force here. We're not going to be concerned with that yet. Boom. So let's talk about the perpendicular radius, right? So we already said and we identified, hey, the length of this board is 8 meters, right? But now I have one triangle, and I don't have to draw anything else because my perpendicular radius is 8 times cosine of 50, because this is adjacent to that hypotenuse. or sorry, this is the adjacent angle to the perpendicular radius times my hypotenuse. So I've got 8 times cosine 50. And again, this is in degree. Make sure in degree mode, not radian mode, because that will mess everything up. This force gets to stay the same. It's still that 5,000 newtons. It's still that 5,000 newtons. So again, to calculate my torque now, I've got my force of tension times 8 times cosine 50. So you'll notice it's the same exact setup that we had. It's just now I've identified how I can figure out that perpendicular component a little bit differently. And since it's side to side, again, the rule of thumb is usually that makes it easier to use the perpendicular radius than the perpendicular force. Either one will work, but I just kind of wanted to walk you through a thought process on how to identify what might be easier to choose. All right, hope that helped. See ya.